The heat of vaporization is another property that is affected by intermolecular forces. Higher intermolecular forces hold liquids together, make it harder for the liquid to evaporate into the vapor. So higher intermolecular forces will generally mean higher heats of vaporization. When we say heat of vaporization, we generally are referring to enthalpy of vaporization, which means heat at constant pressure. So the heat of vaporization, enthalpy of vaporization, we represent that as a delta H VAP, sub VAP. The enthalpy of vaporization is on a mole basis. So if we multiply that enthalpy of vaporization by number of moles, we'll get the heat required for that amount of moles to vaporize. And this will also be the heat of condensation. So it's the same amount of heat whether we are evaporating or condensing that liquid. The evaporation of any liquid is a endothermic process, so we can use this process for cooling down. We use that. We use the evaporation of water for cooling, for power plants, swamp coolers for houses in the desert, and we sweat, which is our natural means of removing heat from our body. Vapor pressure increases as we increase temperature, and this is generally a exponential process. And for materials with a higher intermolecular force, like water has hydrogen bonding with the ability to form a couple of hydrogen bonds for each oxygen. This has the highest heat of vaporization out of our examples here. Ethanol also can do hydrogen bonding, but not as many hydrogen bonds, since one of the hydrogens from water would be replaced with a ethyl group, a 2-carbon group. But it is hydrogen bonding, but it's a little bit lower heat of vaporization. And then ether does not have hydrogen bonding. It's just a dipole-dipole interaction, and not the strongest dipole-dipole interaction. And this is a lower heat of vaporization. So if we just look at vapor pressure also, we see that a high vapor pressure will correspond to a low heat of vaporization. A low vapor pressure will correspond to a higher heat of vaporization. Whenever the vapor pressure equals the current atmospheric pressure, then the liquid can burst from liquid into gas phase inside the liquid, so it can boil, and that temperature where that can occur is called the boiling point. If we're referring to the boiling point at 1 atmosphere of pressure, it's called the normal boiling point, and that's normally what we refer to as the normal boiling point. Now, the vapor pressure is an exponential form. We have found this form. So the vapor pressure of a liquid is equal to a constant times E exponential of negative heat of vaporization over RT, where T will be in Kelvin and R will be in terms of joules. So this shows that our vapor pressure is an exponential form. As we're going to increase the temperature, we're going to be increasing our vapor pressure. We like to put things into linear forms. It allows us some additional manipulations of the equation. So by taking the natural log of this equation and rearranging it slightly, we can get this form of the Clausius-Clapeyron equation, where the natural log of the vapor pressure is equal to negative heat of vaporization over R, gas constant, times inverse temperature plus natural log of B beta. So this shows us that if we plot log of vapor pressure, natural log of vapor pressure versus 1 over temperature, we should have a straight line. This is a form of y equals m x plus b. So it has a form of straight line. So by plotting natural log of the vapor pressure versus inverse temperature, inverse Kelvin temperature, we should end up with a straight line, and the slope of the straight line will be equal to the negative delta H vaporization over R. So if we take the slope multiplied by negative R, we'll end up with the heat of vaporization. We can turn this into a true form. So we can take this equation with two different sets of data points, P1, T1, P2, T2. We subtract the two of them. The y-intercept subtracts out, and we're left with the true form of the Clausius-Clapeyron equation. So we can take one pressure temperature point to help us to predict a second pressure temperature point. So in this case, it would be log of vapor pressure 2 over vapor pressure 1 equals negative delta H vaporization over R times 1 over T2 minus 1 over T1. So often we can use a boiling point to help predict another temperature, or we can use vapor pressure at a particular temperature to predict the boiling point of a liquid. So these are a couple ways of showing vapor pressure versus temperature. So we just plot vapor pressure versus temperature. We're going to get a exponential relationship with the vapor pressure increasing as we increase temperature. If you plot log of vapor pressure versus inverse temperature, we'll end up with a straight line. This straight line has a negative slope on it. So to get the delta H vaporization, we're going to multiply this slope by negative R. That'll end up giving us a positive delta H vaporization and endothermic process, which is what we're expecting, an endothermic process. And this is another way of plotting vapor pressure versus temperature, but using log paper. By using log paper, we turn the exponential form into a linear form. Now we can use our understanding to be able to calculate boiling points and melting points of materials. So the spontaneity of any process is given by the Gibbs free energy. Negative Gibbs free energy is a spontaneous process. A positive Gibbs free energy is spontaneous in the reverse direction, and anything that is at equilibrium will have a zero Gibbs free energy. So Gibbs free energy is the enthalpy minus temperature times the entropy. So if we look at the boiling point of a liquid, if we have this liquid in a sealed container, at the boiling point, we're going to have the pressure, 1 atmosphere, in equilibrium with the liquid. So this is an equilibrium situation. So if it's equilibrium, that means our Gibbs free energy is going to be equal to 0. So we can take this equation here and solve for the temperature, the boiling point, and what we'll end up with is the boiling point is the enthalpy of vaporization divided by the entropy of vaporization. And when we do this, the main thing to watch out for is the units, since we like to show enthalpy of vaporization using kilojoules, and we like to show entropy of vaporization using joules. Melting point, same thing. Melting point is a equilibrium situation. If we have ice and water in a perfect thermos, then the ice will remain in equilibrium with water without any net melting or freezing going on. So being equilibrium, our gift-free energy is 0. We can solve for our melting point, and that will be the ratio of the enthalpy of fusion divided by the entropy of fusion. And again, we have just to watch the units, since enthalpy tends to be in kilojoules and entropy tends to be in joules. So the heat of fusion is the heat required to melt a solid, or heat released when we freeze a liquid. So there will be the same amount of heat in both directions. We tend to show this enthalpy in terms of kilojoules per mole. So if we take our kilojoules per mole, multiply it by moles, we'll end up with the heat that is released when liquid freezes or absorbed when a solid melts. And again, heat of fusion tends to increase with increased intermolecular forces. So the stronger the intermolecular force, the more it holds the material as a solid, and the more energy it tends to take to melt that solid. So when we talk melting points, we are normally talking the normal melting point. Normal melting point is at 1 atmosphere of pressure. Melting points do change with pressure. They don't change as dramatically as boiling points, but they do change with pressure. And we'll see that in a little bit, that some will increase. The melting point can increase with pressure, and some melting points can decrease with pressure. Some materials don't melt, not at room temperature at least. So instead of melting, they can go directly from the solid to the vapor phase. Dry ice would be a perfect example of that. Solid carbon dioxide. Solid carbon dioxide does not melt at 1 atmosphere of pressure. It will just directly sublimate into a gas. And the heat of sublimation is going to be equal to the heat of fusion plus the heat of vaporization under those conditions of temperature and pressure.